Hi, this is Mr. Swanson, and today we're going to be looking at percent composition of molecules, specifically hydrates. And so please follow along with note 6.3 found in the Schoology page. Percent composition of molecules is very similar to any of the other percent compositions you've looked at, or percents that you've looked at, which is just looking at part of a whole. So in this case, we're talking in a molecule. What part of that molecule is maybe oxygen, or what part of it is hydrogen? So we're going to be looking at the mass of each different element inside a compound as a whole and finding the percent. So the formula for percent composition is part over the whole times 100, or the total mass of the given element that we're looking at over the total molar mass of the compound times 100%. So we can take a look at an example here. So we have carbon monoxide, a pretty simple molecule made up of two elements. And so we need to know the total molar mass. So we're just adding up all the individual components, and we get 28.01. Now, we want to find the percent composition of carbon. So you could do 12.01 divided by 28.01 times 100. And when you do that, you're going to get something like, just put my calculator down, 42.88% when rounding to the correct number of sig figs. And so that's the percent composition of carbon. And you could do the other way with the percent composition of oxygen, and you're going to get around 57.12%. Now, it's really important when you're doing these percent composition problems that you're using, and any of the problems for this unit and the next few units, that you're using the periodic table and the periodic table that we gave you, because it's going to have the correct number of sig figs. So get the periodic table that we gave you, and first start by calculating the molar mass of the object. And once you do that, then you can find the individual percent compositions of both of these elements inside the compound. So pause the video, try some on your own, and check back to see what the answers are. Okay, so take a look at my work, and hopefully you had very similar answers to that. Now, you could have done the second part of each problem slightly different. Because you know there's only two elements in the molecule, you could have taken 100% minus the 39.34 to get that answer. So either one of those would have been okay to find kind of the last one if you know the total's always out of 100%. So either way would be fine as long as you got these answers. Okay, and here's one more worked example for you, and again, I'm working some of these to help you save a little bit of time. I do want to point out in this one that 1.01, the mass of hydrogen, only has 3 sig figs, so that's why the answer's only rounded to 3 sig figs for this. But hopefully you can follow through in this work, and you're starting to understand how you can find the percent composition of any element in a given compound. Now, I first want to remind everyone what a salt is. And so a salt is just an ionic compound. And an ionic compound is made up of cations and anions, or positives and negatives. So a salt is any kind of combination of positives and negatives that come together to make a neutral compound. So you might get something like this. Okay, so there's your salt. Now, you notice that there's a lot of positives and negatives right there, and so water is very attracted because we have those dipoles. So water is very attracted to this molecule, and so we get what we call hydrates. So a hydrate is when you have a salt with the positives and negatives where water is chemically bonded to that, and that would be an intermolecular force, right? We've talked about that could be hydrogen bonding. Now, or just any dipole-dipole interactions. Now, you can see here, and this is a very common salt, copper sulfate, and when it has water bonded to it, it is actually blue. And so you can see that the oxygen is kind of surrounding the positive ions down here, and the hydrogens are pointing more to the S, or sorry, the O's on SO4. So you can see how water is chemically bonded. And so the hydrate has a bunch of water on that. And in this case, there's 5 molecules of water for every 1 molecule of copper sulfate. So we're going to talk more about hydrates and kind of the difference between when they're anhydrous or when they're a hydrous salt, so with water and without water. Since there's water in the air, it's really easy for these molecules to kind of soak up this water. And so a lot of times they're going to be presented as a hydrate, so with the water chemically bonded to it. And it takes energy, and so thus it's expensive, or at least costs some money, to have a pure anhydrous form. A pure form, which is kind of showing you right here, without water attached to it. But this can go back and forth, right? So we can get an anhydrous form that's without water, but over time, especially if you don't leave it, if you leave it out or if it's not sealed, it's going to go back to its original form. And in this case, you can see a color change. There won't always be a color change between the processes, but in this case, there is. So percent composition is going to work very similar for hydrates. And so the first thing you want to do is you want to find the molar mass of kind of the whole thing. So you're adding the molar mass of the copper sulfate and then the molar mass of water. But in this case, there's 5 waters. And so you're going to have to combine that all together. So pause, see if you can figure it out, and then I'll have the worked solution for you. So in this problem, a couple things I want to draw your attention to. Number one, always write the units. So putting grams per mole is very important for this, and we will give you points on the test for doing that, or I guess take points off if you don't do that. The second thing with the hydrates, it's 1 molecule of copper sulfate bonded to 5 molecules of water, and so you need to include 5 H2O with that. So if this is wrong, obviously this answer is going to be wrong as well. So make sure you do 5 H2Os. Even though, if you go back to the previous page, it shows you really a good kind of, or 2 pages before, a good view of what it means to have water chemically bonded to it. Okay, so now we're getting into kind of the final overall question. You understand what a hydrate is, you understand how to find molar masses, you understand what percent composition is. So to put it all together, what's the percent composition of water in copper sulfite hydrate, which is copper sulfate pentahydrate, you'd say it. So that 5, we use the prefixes to say pentahydrate. Anyways, in the previous slide, you figured out a lot of the information that you need to know to solve this. So just kind of drawing from that information, the total molar mass of the whole compound is 249.72 grams per mole. And we want to know the percent composition of water. So how much does water contribute to the overall mass of this hydrate? And so the mass of the water on this is 90.10 grams per mole. The grams per mole are on the top and the bottom, and so they're going to cancel out. And so the percent composition is going to be unitless. It's just going to have a percentage. Okay, and so we can do that math then. And so 90.10 divided by 249.72 times 100. And so water contributes to 36.08% of this hydrate. Now that's a pretty good percentage of the mass. And so let's say you were adding this molecule in for a chemical reaction. Well, you think you're adding in a lot of copper sulfate, but really you're adding in a lot of water. And so maybe you're not going to have as much of the reaction happen as you think because it's a lot of water in there and not the copper sulfate instead. So you want to use this idea to account for stuff like that, like when you're doing a chemical reaction. Also, like when you're just weighing something out. And so you might need to add more to account for how much water is in the sample. So hopefully you understand the percent composition piece and the hydrate piece and how to put it together.